This video is about adding vectors in 2 dimensions. I'm Mrs. Estock. Let's get started. As a quick review, in the last unit we talked about scalar quantities versus vector quantities. Remember, scalars are quantities that have only magnitude or size. They do not have direction. Scalars include values like distance and electric charge and temperature, things that have no direction associated with them. Whereas vectors have both magnitude and direction. Vectors we've talked about include displacement, velocity, acceleration, and force. Vector quantities have to have both magnitude and direction, and when adding vectors together, we have to take their direction into account. So far, we've only added vectors in 1 dimension, meaning the vectors have been parallel to each other. And when the vectors were pointing in the same direction, we would add together their values to get our resultant vector. And when the vectors were in opposite directions, then we would subtract those vector quantities to get our resultant vector. We looked at the example below, where if you have a 50 mile per hour vector pointing to the east and a 40 mile per hour velocity vector pointing to the west, the resultant of those would be equal to 10 miles per hour east. We get that by subtracting the values because the vectors are pointing in opposite directions. But in this unit, when we talk about projectiles, we're dealing with objects that are moving in 2-dimensional space, so both vertically and horizontally simultaneously. In order to add vectors in 2 dimensions, we need to review our head-to-tail method, but this time for 2-dimensional motion. The head-to-tail method consists of connecting the head of one vector to the tail of the other vector, where the head is the arrow point and the tail is the end of the arrow. Then we draw in our resultant vector, starting from the tail of the first vector, or at the origin where you began, and the resultant points to the head of the last vector you drew. So it's a straight line pointing from start to finish, where you started drawing to where you ended drawing. So let's say we have 2 vectors to add together here, vector A and vector B. First, we would need to arrange these vectors head to tail. So that the tail of vector B is connected to the head of vector A. Notice we have not changed the length or direction of either of these vectors, A or B. It's almost like you're picking up the arrow and placing it down in a different location, maintaining its size and direction while doing so. This is what we call the head-to-tail method. So the head of vector A is drawn connected to the tail of vector B. From here, we can draw in our resultant vector. It starts at the origin, or at the beginning of the first vector, and points to where you finish drawing the head of the last vector, or the end point. So it's a straight line from start to finish, pointing to where you ended. Let's give this a quick thought experiment. What if, instead of adding A plus B, I added together B plus A? Would I still get the same resultant? Let's try it. This time I'm going to add together B plus A using that head-to-tail method. So this time I started by drawing vector B, so the tail of vector B is my origin. And then I drew the tail of A connected to the head of B. And if I draw my resultant from where I started at the tail of B to the head of A, hey, the resultant is identical. It's still the same length and still pointing in the same direction. So it turns out it doesn't matter what order you add these vectors in using the head-to-tail method. You will still get the same resultant. Let's break down this head-to-tail method step by step, starting with step 1. If we were using the head-to-tail method to graphically draw this vector addition to scale on a piece of paper, the first thing we should do is choose the appropriate scale. The best choice of a scale is one that will result in a diagram that's as large as possible, but still fits on your sheet of paper. It's kind of like Goldilocks. Not too big, not too small, just right. Once you've determined your scale, make sure that you write it down on your paper, clearly stating what your scale is equal to. For example, you could write down our scale is that 1 centimeter is equal to 20 meters, meaning that every centimeter you draw on your piece of paper represents 20 meters worth of displacement. Next, find a location on your paper to start drawing. Think about how your vector diagram is going to look before you start drawing to make sure that you've picked the correct location to begin. You want to leave yourself enough room to be able to draw your vectors head to tail on your piece of paper without running off the edge of the page. Once you've picked your starting location or your origin, draw the first vector to scale in the indicated direction from the question. Once you've drawn your first vector to scale, starting from the head of that vector, draw your second vector in the head to tail method. So the tail of the second vector is connected to the head of the first vector that you drew. After drawing the two vectors head to tail, make sure to label them with the magnitude and direction of each vector. If there are any more vectors to add together, for example, if you're given 3 or 4 vectors to add together head to tail, keep repeating steps 2 and 3 until all vectors are drawn to scale and they're all drawn head to tail. Next, draw the resultant as an arrow that points from your starting point to your ending point. So your resultant arrow should point from the tail of the first vector that you drew to the head of the last vector you drew. Label this vector as the resultant or with a capital R. Next, we need to measure the magnitude and direction of your resultant vector. Using a ruler, measure the length of your resultant and determine its magnitude by using your scale to convert centimeters back into the original units. Treat your scale as a conversion factor and treat this like a unit conversion. So for example, if you use your ruler to measure the length of your resultant to be 4.4 centimeters, that's not your final answer for that resultant. You need to convert those units from centimeters back into the original real units that were in the problem. So we can use our scale, that 20 meters is equivalent to 1 centimeter, to convert this back into meters. So in this case, 4.4 centimeters represented 88 meters of displacement on our scaled vector diagram. Last but not least, we have to measure the direction. If you're adding vectors in 2 dimensions, then your resultant will probably be at an angle. It's not sufficient to just say that it's pointing northeast or southwest. You need to get an exact measurement as an angle theta using your protractor. Using your protractor, line up the 0 degree mark with one side of your angle that you're measuring, and make sure that you're starting at the origin with your measurement. And from there, rotate clockwise or counterclockwise, depending on the direction of your resultant, to measure the angle that it is pointing at. The angle that the resultant is pointing at is the direction of the resultant. So those are the steps for the head to tail method. Let's put it into practice with a sample problem so you can see it in action. Let's say that a girl walks 60 meters east and then 80 meters north. What is the resultant displacement of the girl? First thing we want to do is draw our scale, or write our scale down on our piece of paper. For this problem, I'm going to say that my scale is 1 centimeter is equal to 10 meters. So for every centimeter drawn on my piece of paper, that's going to represent 10 meters of displacement. I can use that scale to figure out how big to draw my vector arrows when I'm adding them head to tail. When I use my ruler to draw the 60-meter east vector, using my scale, I'm going to convert from meters to centimeters. And now I can see that I'm going to draw a 6 centimeter long arrow for the eastward pointing vector. And if I do the same thing for the northward pointing vector, I can see that I'm going to draw it 8 centimeters long. Next, I get out my ruler and I measure my first vector pointing to the east to be 6 centimeters long. Make sure that we draw it as an arrow pointing to the east, and it measures to be 6 centimeters in length. Next, I'm going to draw my 80-meter north vector by moving my ruler to be perpendicular to my original vector pointing east, and I'm going to draw my northward pointing vector with the tail starting at the head of the vector that I have on my paper. So picking up where I left off from that eastward pointing vector, I'm going to draw the northward pointing vector to be 8 centimeters in length and added head to tail to the first vector. Now I have my 2 resultant vector arrows drawn head to tail. From here, I'm going to use my ruler to draw a straight line from the origin, or from where my first vector started, to my ending point where my last vector ended. Also, I should stop and think, what do I get when I add together east and north? Well, east plus north equals northeast, so my resultant should be pointing northeast. Once I've drawn my arrow for my resultant vector, I'm going to use my ruler to measure its magnitude or length. The length of this resultant vector arrow is 10 centimeters. But remember, that's not our final answer because we've drawn everything to scale. So now I have to take my measurement of that resultant vector and convert it from centimeters back into my original units. 10 centimeters drawn on my piece of paper represents 100 meters of displacement. So now I have the magnitude of the resultant vector, but I still need to find the direction. So I get my protractor out and I line up my protractor so that one side of the angle lines up with the 0-degree mark, and then the resultant points to the angle that I'm measuring. Make sure you're looking at the scale that starts at 0 on your protractor to measure this angle as the direction of your resultant. And in this problem, it should measure to be about 53 degrees. So our final answer is that the resultant is 100 meters at 53 degrees north of east. That is our final answer. So this practice problem is an example of using the head-to-tail method to add vectors graphically to scale. You could also solve this problem mathematically. Since we are looking at a right triangle, to solve for the angle, or if we have the angle and need to solve for any one of the sides, we could use trig. We could use sine, cosine, and tangent to solve for any of those unknown values. And we can also make use of the Pythagorean theorem, a squared plus b squared equals c squared. These formulas are on your reference table. And if we were to apply these formulas to the same question we just looked at, we should get the same answer. So let's see if we do. When you're solving these problems mathematically, you do not have to draw them to scale, but I would suggest drawing a diagram to help you in your solution. So on my paper, I would draw a quick sketch of 60 meters plus 80 meters, added head to tail, keeping the directions in mind, and showing that my resultant vector is pointing northeast at some angle. I could use Pythagorean's theorem to solve for the magnitude of the resultant. A squared plus b squared equals c squared, where c is the resultant vector, the hypotenuse. And if I plug those values into the formula and solve for r, I get the same answer, 100 meters as the magnitude of my resultant vector. From here, I can use any one of the trig formulas to solve for the angle theta. In this case, I chose to use sine. First, I start out by writing the equation. Sine theta equals opposite over hypotenuse. The side opposite my angle theta has a magnitude of 80 meters, and my hypotenuse, which I just solved for as r, has a magnitude of 100 meters. I can rearrange this to solve for theta by taking the inverse sine of both sides, and I get the same answer. Our angle theta is equal to 53 degrees. So either way you do it, you get an answer for the resultant vector of 100 meters at 53 degrees north of east.